Okay, hello everyone. So it's my great honor to introduce the Professor Shubham, and he is an assistant professor at Carnegie Mellon University in the Robotics Institute. And he is a part of the computer vision group, and he's very interested in the building perception system and can infer the spatial and the physics architecture in the world we can observe. And for today, he will provide a talk about probabilistic pose prediction in our workshop. Welcome to the Professor Shubham.
Yeah, thanks for the introduction. I hope I'm audible. If not, please feel free to tell me to speak louder or something. So it's a pleasure to be here. I'm sorry I couldn't be there in person, but hopefully sort of the remote, now that we're all familiar with sort of Zoom talks, hopefully this won't be too bad. So yeah, I think the workshop was titled on sort of SLAM and robot learning, but today I wanted to give you some updates on a slightly different research agenda that we've been following, kind of related to estimating cameras, but in a rather different setup compared to what you would see in sort of a normal SLAM setup. And so in that context, I want to talk about this line of work from our group on probabilistic pose prediction. For the last couple of years, I think in my group, we've been looking at this task of what I call the Craigslist problem, which is anyone who wants to sell any object they have on Craigslist will naturally upload a small number of images of that object. So for instance, there'll be these 4 images of a desktop monitor that, let's say, someone wants to sell. And given this, you want to be able to get sort of a high fidelity 3D reconstruction of this object. And of course, the goal is we want to be able to do this from a few casually captured images. So again, an average user will not painfully go around because they don't really know what sort of data makes a SLAM or SFM system work. They'll just take 3-4 images of an object that they want to sell. And it could just be a generic object, right? This is something, they may sell arbitrary toys, etc., etc. And so we want systems that can go from the small number of images to 3D reconstructions of the object. And really this problem, I think, kind of breaks down into 2 sub-problems. One is, given just a small number of images of such a generic object, we want to be able to register these images together, estimate pose of all these images from just a handful of views. And secondly, given our understanding of these views, if we have understood poses, we want to be able to then reconstruct the 3D structure of the underlying object. In today's talk, I'll sort of focus on the things on the left, but I want to sort of give you a brief highlight of some results from our group of the problem on the right, just to convince you that if we can get poses, we can sort of eventually use these to get 3D. So here's this sort of a result video of one of our recent projects. Feel free to go and look at the website that's sort of cited at the top. But given just a handful of images, sort of 2 images, or actually 3, 4, etc. images, we can get reasonable 3D reconstructions of generic objects. But all of this is assuming that we know the camera poses corresponding to these 2, 3, 4 input images that are available as input to the system. And so really, I would say we made a lot of progress in being able to infer 3D reconstruction given a small set of views. Some of the work from our group that I cited, some other work going on using generative models, etc. for this has let us make huge leaps in 3D reconstruction. But all of that assumes the camera poses corresponding to the input view. So I really argue that almost the harder task, given the current state of the field, is really how do you register these cameras? Given a small number of images, how do you estimate corresponding camera poses? Okay, so sort of formally, the task that I'm going to talk about today is, given a small number of images, we want to output sort of 60 camera poses corresponding to all those images. Okay, and when I sort of pose the problem this way, especially to this crowd, hopefully all of you just think that, by the way, we will assume that so the world orientation is aligned with the first image, just to make sort of the problem a bit well-defined. But as soon as I pose this problem that I want to go from a few images to the 60 poses, hopefully this crowd just immediately thinks of, well, Colmap sort of does that already for us, so why don't we just use that? And that's a very valid thought. And in fact, Colmap is sort of an amazingly powerful algorithm, or in general, structure for motion is an amazingly powerful class of algorithms that, given many images of a generic object, can let us understand the poses, can even give us sparse view reconstruction. But unfortunately, in sort of the setups that we are interested in, whenever we test Colmap, it's just not robust enough, because even if you have something like 10 images and we actually want to deploy these with even fewer images, there are just not enough correspondences between these views. So you might have 10 images or 4 or 5 images from sort of a 360-degree-ish field of view. And it just any method relying on these bottom-up correspondences is just not robust enough under these sparse views, which have a small amount of correspondences. And so, while the task that we are studying is very much related to things that structure from motion tackles, under sparse views, these bottom-up approaches really, really struggle. And so if bottom-up approaches struggle, the obvious thought one might have is, let's just have data-driven top-down prediction, and that can lead us to more robust inference. And this we have seen time and time again for other problems, segmentation detection, where we moved from bottom-up methods to top-down methods and have sort of gotten robust prediction in all those scenarios. And so let's try to embrace that idea and have a learning-based approach that can presumably be more robust to sort of not having enough bottom-up matches. And we can go ahead and do that. So here is just an attempt at designing such a top-down prediction approach. So let's say we have n images. We compute some encoding of them. You can sort of use your favorite ResNet, extract some features of those images, and then feed all of them to a transformer, which can do this joint multi-view reasoning, can look at all images in context of all other images, predict some per image features or tokens. And then at the end, you can just say that, okay, give me a rotation and translation for each of these images, assuming the first image's identity, and you can sort of train this network that way. Right. So here is a very simple pose prediction approach that one might design if we wanted to have a top-down prediction architecture that sort of learns pose prediction in a data-driven way. Unfortunately, naively doing this just doesn't work. So here is just a sample result where the black cameras are the ground truth, the red cameras are the predictions, and you can see there's just a huge mismatch between the black and the red cameras. And that's because, I've chosen this object a bit carefully. It's a symmetric object. It's a ball that has a lot of repeated structures and ambiguities. But anytime you design a feed-forward prediction method, it just struggles to predict the right answer because there are sort of many possible solutions. There are symmetries in this object. You might be partially observing it. You might just not be sure that, whether a particular camera is viewing the front of the ball or the back of the ball because there are a lot of repeated structures. And if you ask any regression approach to predict a single answer under such uncertain scenarios, it's basically doomed to fail. Just as an illustration of this, and sort of maybe I'll walk through this quickly. If you have a direct prediction approach, you train it using L2 minimization error, it basically predicts the mean of distributions. So it will give good answers if the distributions are simple. It will give bad answers if the distributions are more complex. Instead, what we are advocating is to have sort of probabilistic modeling, hence the title of the talk, where instead of directly predicting a single answer, you say, okay, I'll try to model the distribution of the underlying variable and then try to infer some mode in that. And if you can do this well, then for simple distributions, of course, you'll still end up at a good answer. For more complicated distributions, again, you'll maybe end up at this mode, maybe you'll end up at the left mode, but you'll still end up at solutions that are better than just the mean-seeking direct predictions. And so this is, again, a very, very generic slide. You can ask yourself if this is valid for your problem as well, but we want to instantiate these ideas for the task of post-prediction. And to do this, we go back to this framework and have actually a very, very small change. So instead of directly regressing the rotations and translations, we say, okay, let's learn an energy-based model to capture the distribution of relative rotations. So we take the features for image I, we take the features for image J, and predict just a score that tells us if the score is high, then that means the relative rotation is likely. If the score is low, then that means the relative rotation is not as likely. So it's just unnormalized log likelihood, and we can sort of train this model using multi-view data where we know relative poses between images. And here are just some visualizations that I'll show for a couple of slides. So I'll just walk you through how to interpret these charts. So given two images, so there is one axis which corresponds to sort of changing the yaw. There is one axis in these charts that corresponds to relative rotation where we are changing the pitch. And the color of this point, which is right now blue, can change and indicates the role. So because we want to show these 3 degrees of freedom in a 2D plot, we're using the color to show you the 3rd degree of freedom. And so given these two images of a couch, our model does predict some distribution, sort of a very image under very poor lighting. So the model is still confused a bit, but it predicts these 4 modes, which are roughly corresponding to sort of 4 orientations of the couch that it can have. And the open circle tells you sort of the right mode. For this other image of a sandwich, which perhaps is a bit more texture, is taken under better lighting, the model is more sure about the right mode. But I think the example that I like the most is this one, where there is this rather symmetric object, and the model predicts basically that, okay, there can be arbitrary sort of roll, and that's why you see all these colors that are centered around 0, 0. And so training it this way can allow the model to model the distribution as opposed to trying to give a single answer, which it will not do a very good job at if there is such multimodal uncertainty. And here's just a visualization. So for instance, if we focus on the bowl on the right, there are some symmetric structures. So the model is a bit uncertain about the precise relative rotation. Where it stops, it's kind of confident that it's identity, but it also thinks there may be some other modes because the object is a bit symmetric. And maybe I'll sort of skip this. But at the end of the day, once we have modeled these pairwise distributions, we can just say, okay, let's optimize for rotations that maximize the overall score. So we start with arbitrary rotations and do a coordinate ascent-based optimization to optimize R1 to Rn, such that the configuration that we get to has sort of the maximum possible pairwise score when summed across all pairs Ij. And we can just easily do this by coordinate ascent. Here, let me just visualize one iteration for you. So if we have 5 images, we have a current set of rotation hypotheses. In each iteration, we pick one rotation to update. So here we have picked sort of the red camera to update. We sample sort of hundreds of hypotheses for it, score all of them, and just update the red camera to the best scoring hypothesis. And we sort of do this a few times in practice, about 20, 30 iterations suffice. And that basically gives us these global rotations across images. Okay. And you might notice that I've not really talked about translation estimation so far. And the reason is that we can actually get away without modeling uncertainty in translation estimation. And so the high-level idea is just a high-level reason why we can do this is if you dig into what translation actually means. So when we write RNT, we actually means that RNT transform world points to camera points in this way. And so if you dig down, that means that camera translation is actually the location of world origin in camera frame, and it's not sort of the location of camera in world frame. So maybe let me play this GIF again. As I'm moving the camera, the translation TI of this camera is not really changing because the world origin is at the same point in the camera frame. And so, but of course, changing the world origin does change the camera, but rotating the camera around the world origin does not. So sort of long story short, if we choose a wisely centered coordinate frame that has sort of a conveniently chosen world origin such that the ambiguities are only in rotation around it, we can get away without modeling uncertainty in translation because we have decoupled uncertainties in rotation from uncertainties in translation. And maybe I'll sort of skip a lot of details so just I can show you more results. But in our paper, we say that there is this particular look-at centered frame that we should choose. But once we do that, we can just frame translation prediction as a regression problem and not worry about modeling uncertainty, and that sort of suffices. So we can just take the features from the ith image, predict translation, and we also take the features from the first image because we just use that to determine scene scaling. So we choose a coordinate system such that the norm of translation of the first image is 1, and so we feed those features in as well. But yeah, once we do that, our system, just like Colmap, can give us 60 pose predictions given a small set of images. So here's some comparison, but actually I would argue that Colmap is a bit more precise than our system when Colmap works. The main issue with Colmap is that we had to struggle really, really hard to find these examples where Colmap does work very well. In fact, for most scenarios, if you give us a small number of images, our method can robustly infer poses that are pretty accurate, so within 5-10 degrees accuracy. But Colmap, for most of these scenarios, just does not converge or give you any meaningful results. And we also quantitatively evaluate this on this Co3D dataset, where I'll just show you some lines, but the green line corresponds to our method, and it's pretty accurate. So on categories that it has seen, it performs at about 80% accuracy, or 85. And what is more impressive for me is that even on categories that it has not seen, so completely new objects from unseen categories, it can still give you accurate poses about 75% of the time. And what that lets us do is just try our method on self-captures. So here are just some objects that have nothing to do with any of our training data sets. This is just one of our students or me capturing some images. And given these, our system can infer reasonably accurate poses. So if you look at the Gandalf statue and you look at the pink camera, we've taken it a bit from the top, and the method does understand that, and all of the relative configurations are kind of correct. And again, just some more results on self-captures which have nothing to do with any of our training data. Our model can give you pretty accurate relative poses given these small set of images. Yeah, and as I said, we were trying to get these poses so we can use this for downstream reconstruction. Here's just a proof of concept that if you go around CMU, you can sort of find a lot of stray robots around. You can capture a few images of any of these robots, and sort of, here's an image of some images of a Baxter robot that we got cameras from, and then fed it into some reconstruction pipeline that just optimized those cameras slightly and could give us a pretty decent reconstruction of that object. And yeah, so I think so far I talked about this energy-based modeling, and I'll just briefly give you sort of a couple of slides of a recent project, which will hopefully be up on arXiv in a couple of weeks, where instead of energy-based modeling in terms of global rotations and translations, we were looking at diffusion-based modeling in terms of equations of these rays, and it can give us slightly better results because it allows us to also use these patch-wise features unlike just global features. But yeah, just a brief advertisement. So hopefully this will be out on arXiv in a couple of weeks. So you feel free to look at that. And again, this works across, if you give it 5 images, it can sort of diffuse the rays corresponding to all these cameras and give pretty accurate cameras that are actually a bit better than the previous project I showed, just because it can use both bottom-up reasoning in a probabilistic inference framework. And yeah, I think with that, I would like to acknowledge sort of Jason, Amy, and Deva. So all of this work was in collaboration with Deva's group, and Jason and Amy really did all the hard work. So if you have any questions, feel free to reach out to sort of Jason and Amy. The code and models for the projects that I talked about are already available. So in particular, RelPose++ is the latest and greatest model that we have, which I would really encourage you to just go and download. We also have a demo where you can just upload any images of an object around you, and sort of I'm reasonably confident that we'll do a good job at inferring relative poses for a generic object whose images you can upload. So yeah, please do try that out. Yeah, I'm happy to take maybe a question, but unfortunately I might have to run to another talk in a couple of minutes.
Okay. Thanks for the Professor Shubham. So probably we only have one question. So
yeah.
One has a question for the Professor Shubham. Okay, so probably I have one question for Professor Shubham. So basically, for the real pose, do you think what's your interpretation if you test the real pose for other kinds of camera models, such as the visual camera or other camera model? Is it still working?
Yeah, so that's a great question. So the current model might not work as well because it's just been trained on a specific class of cameras. But I think if you could also fine-tune it with a small amount of other camera data, I'm pretty sure it will work as well. So out of the box, it won't work as well. But if you fine-tune it with a bit of fisheye data, there's nothing in the model that is sort of specifically assuming a camera that is, perspective. And in fact, the later work that I pointed to, which is just associating equations of rays, actually might also be a good candidate for generalizing to other cameras, because it will just predict ray equations for a lot of pixels, and then later you can just recover the camera model from it.
Okay, got it. Thanks for the Professor Shubham for the great talk again. Okay, thank you. So for the